Dear students, after studying this module, you shall be able to have the basic knowledge of catenanes and rotazanes, and also you shall learn about the preparation of catenanes and rotazanes. You shall also learn about the pi-pi stacking interactions in catenanes and rotazanes, and also learning about the catenanes and rotazanes in the form of molecular necklaces. Now students, let us begin this topic of rotazines and catenanes. Catenane is a compound consisting of two or more rings that are interlocked mechanically without there being necessarily any chemical interaction between the two. Generally, without breaking a chemical bond, the rings cannot be separated. Rotazanes, on the other hand, consist of a long, fairly linear molecule threaded through a macrocyclic ring, like cotton through the eye of a needle. Similar to catenanes, rotazanes also cannot decompose into ring and chains without breaking chemical bonds. Hence, the bulky groups terminated the linear chain part of the molecule, and it is too large to fit through the cyclic fragments. Rotazanes without such physical barriers in which the thread can leave the needle are known as pseudorotazanes, and these pseudorotazanes are necessary precursors for the formation of both rotazanes as well as catenanes. Now students, having introduced the topic of rotazanes and catenanes to you, let us now come on to the nomenclature of catenanes and rotazanes. The nomenclature of catenanes is decided by the number of rings, that is, how many number of rings are interlocked to one another. For example, 2-catenane consists of 2 interlocked rings. This is shown to you in the figure. Analog, that is ane word used in the end is similar to alkanes, and a catenane is mainly consisting of an organic fragment, and it really consists of moieties, that is the hydrocarbon in nature. The terms N-catenand and N-catenate are also used analogously with cryptand and cryptate for a metal center which is suitably interlocked in the ring system of a catenane acting as a ligand. The catenand is the free ligand that forms a catenate complex in the presence of a metal center. Rotazanes can be named in an analogous manner too. Now, if you consider this figure carefully, then you can see how the nomenclature of catenanes, rotazanes and pseudorotazanes has been done. Now, you can see that in case of 2-catenanes or 2-catenand analogous to alkane, that means 2 rings are interlocked with each other. You can then see the 2-catenate, that means there is a metal center which is present in the rings which are interlocked. Again, 3-catenane has 3 rings interlocked to each other. Then you have 2 pseudorotazane and 2 rotazane and 3 rotazane, and the structural difference between the pseudorotazane and rotazane can be clearly noticed here in this figure. Now, the synthesis of catenanes and rotazanes is our next topic, which is very important. Typical synthetic procedures consist of the templated self-assembly of a pseudorotazane, that is having a kind of host-guest complex, using electrostatic or hydrogen bond forces with metal ion, followed by ring closure, that is catenanes, or termination at one or both ends of a bulky group, that is in case of rotazanes. Now, consider a general synthesis of catenanes via host-guest chemistry. You can see this linear line molecule is the guest and this ring is the host. By self-assembly, the Rotazines and Catenanes both can be formed. Here again a reminder, as I told you, that Pseudorotazines, they are the precursors of both Catenanes and Rotazines, and this figure clearly shows that. There are two approaches for the Catenane synthesis. First one is the statistical approach and the next one is the direct synthesis, in which the approaches relying on self assembly are there, that is on the direct synthesis. The statistical approach relies on the small chance that microcyclization may occur while a linear precursor is threaded through a macrocyclic component. This type of statistical approach was found first in the synthesis of 2-catenane in the year 1960. From cyclization of a long chain diester while threaded through the annulus of a deuterated C34 cycloalkene. Now we are showing the same in scheme 1 that you can see. Although the overall yield of the catenation reaction was less than 1%, but the existence of the catenane was confidently established that it was formed. For the Rotazine synthesis, the statistical approaches have also been used. Rotazines and Pseudorotazines have been synthesized by refluxing at 120 degrees Celsius, that is a range of cyclic hydrocarbons of between 11 and 39 CH2 groups, that is methylene groups, with a linear triphenyl methyl stoppered components to give rise to Rotazines. At this temperature of 120 degrees Celsius, larger rings are occasionally able to slide over the end of triphenyl methyl stoppered groups. On cooling this system, a low yield, that is less than 2% of Rotazine was obtained. At room temperatures, C29 macrocycle containing Rotazine is stable with respect to slippage back to constituent components, whereas macrocycles with chain length of C33 and upwards are extremely labile at this temperature. C28 macrocycle attaches to surface a resin through a covalent bond which reacts with the dumbbell shaped components and provides a total of 70 times more stable Rotazine that can be cleaved from the resin and purified to result in an overall yield of 6%, which is higher than the previous methods that we have studied. Now you can see this in the scheme given to you here in figure, that is a statistical Rotazine synthesis. First is from the product from the solution and second is from the analog prepared in higher yield, that is 6% on a solid support that is called a resin. Now let us come down to the Rotazines and Catenanes, which involve the pi-pi stacking interactions and how these interactions are helpful in their study. A much more directed approach is very much needed due to the low yields which are obtained in the statistical approach for the synthesis of Catenanes and Rotazines, because as you have seen, the maximum yield that could be obtained on the solid phase was only 6%. So you need a better form of synthesis. The clear strategy towards a directed Rotazine and Catenane synthesis is to encourage a self-assembly of the reactants before the cyclization or stoppering reaction that covalently fixes this array together. For the much greater coupling in the desired fashion when they react, the reactants are predominantly coupled in solution as a self-assembled host-guest complex. That is, a relatively large binding constant is with it. Generally, the pre-reaction host-guest complex is a pseudorotazine and it forms a self-assembled template for the covalent synthesis of Rotazines and Catenanes. The strong pi-pi stacking interactions occur with the aryl corantes and the herbicide para-K, resulting in solid state and solution incorporation of the electron deficient guest within the Coran ring. The two pseudorotazane formed due to this insertion of para-K within the macrocycle. The guest is electron deficient and the host is electron rich in the case of para-K. The stability of pseudorotazanes increases with increasing chain length. Now, this is shown in the figure. There is electron rich podans of the type ROC6H4OR, where R is the methyl group as shown in figure number 10.68, and where R is equal to H brackets OCH2CH2 and the N factor after closing the bracket, where N is equal to 1 to 4 as shown in figure 10.69. Now, they are incorporated into a rectangular box made up of two para-K derivatives, as you can see in figure 6.81, to give another type of 2 pseudorotazane. Compound 6.81 is famous as Stoddard's little blue box. Now, you can see the structures and their numbers which are stated in these figures. They show you the various types of pseudorotazanes. Based on the former approach, the higher pseudorotazanes such as 3-pseudorotazane have been constructed rather like threading beads onto a string. The pi stacking and charge transfer interactions between the aryl rings stabilize the tetracatonic cyclophane. Now, you can see this here, the 3 rotazanes and the interactions which stabilize it. The tetracatonic cyclophane is also stabilized by the solvation of positive charge on the blue box by the crown oxygen atoms and CHO hydrogen bonds formed from a relatively acidic aryl CH protons to the crown oxygen atoms. All the complexes which contain this type of binding motifs show the characteristic orange color due to charge transfer interactions. For the preparation of rotazane from pseudorotazanes, the most clear protocol is to attach a bulky substituent to the open end of the threaded molecule. The overall procedure is termed as threading. Now, this can be shown in the figure. You can see here the synthesis of rotazanes via the self assembly of electron rich and electron poor aryl fragments. Now, students, take another example, that is the preparation of triisopropylsilylated 2-rotazanes by the reaction of diols and bis bipyridinium receptor with triisopropylsilyl trifluoromethane sulfonane, also popularly known as the triflate group, in the presence of lutein provides 21% yield of 2-rotazanes. Now, notice that this yield is higher than the 6% which was obtained on the resin. This is shown in the next figure. The same compound can also be prepared by the clipping route, and this afforded 14% of yield using a preformed triisopropylsilylated thread. Now, you can see this in this figure which shows you the synthesis of the 2 rotazanes as I described above via the clipping approach. The final approach to rotazanes is by slipping for the passage through the microcyclic ring upon careful heating or refluxing by using a terminator group. But at lower temperatures, a sufficient amount of energy is definitely required to break through the conformational barrier. An alkene metathesis was used for the synthesis of 3 and 4 rotazanes. Porphyrin derived macrocycle has been a very strong affinity for pyridinium derivatives in dichloromethane. Now, porphyrin in general also shows a very high affinity for bipyridinium derivatives which is present in dichloroethane. 3 or 4 rotazanes developed by the alkene cross coupling reactions between 2 pseudorotazane followed by the Grubbs catalyst. With this reaction, students, only 25% yield of 3 rotazanes was achieved. for the improvement of yield of 3-rotazine by the use of excess microcycle being present in the reactant resulted in the formation of 4-rotazine as well as 3-rotazines, that is a mixture of products was obtained. This might have been possible due to the thread that binds the two macrocycles before the coupling stage. The manganese 2 complex of the porphyrin containing macrocycle is a very good catalyst for epoxidation, that is addition of an oxygen to a alkene to give a 3-membered COC ring of alkenes. For such type of oxidation, the idosyl benzene, that is PHIO, an oxidizing agent, was used. For the addition of oxygen atoms to a threaded polybutadiene substrate, the toroidal complex may act as a processing catalyst analogous to DNA polymerase. The schematic process is shown here to you, where you can see this is basically a cartoon representation of manganese 2 complex of the compound 10.72, here acting as an epoxidation processing catalyst to give rise to the product. The 4 and 5 catenanes are also prepared by following clipping route. For the synthesis of 5-catenane, a 2-step process involving clipping of the precursors around 2 molecules to give the 3-catenane. Further clipping of the 2 molecules of this 3-catenane provides the desired 5-catenane as a product. However, due to the conformational mobility of the crown ethers, the fortuitous scheme ended in failure. This synthetic strategy was modified for the desired product under atmospheric pressure using the same strategy with the intermediate sized crown ether providing the intermediate 3-catenane in only 3.5% yield. Finally, this protocol afforded 3-catenane in the last step. This is now carried forward to the second stage to give rise to the 5-catenane. Now also note that under high or ultra high pressure conditions, clipping of another molecule with 3-catenane gave 22% yield of 4-catenane and a trace yield of 5-catenane, which we actually desired. For the improved yield of 5-catenane, some other changes have been done and finally achieved by another change of crown ether and the substitution of aryl ring in the macrocyclic compound for the 1,5-dioxynaphthalene analog. The resulting molecule was called as olympidiane or olympidane due to its resemblance with the International Olympic Games symbol, which has rings interlocked with it also. The analogous 4-catenane was also obtained in 31% yield. 5-catenane and its formation was characterized by proton NMR spectroscopy, which shows the highly symmetric property at 60 degrees Celsius temperature due to fast interannular circumrotation of all components. At room temperature, a broad spectrum was obtained, while at 0 degrees Celsius, 2 signals of small cyclophanes were obtained because all motions are restricted at lower temperature. These 2 signals of small cyclophanes correspond to freezing out of the rotation of these components as stated by me before. Now students, let us look at another aspect of rotazines and catenanes after having learnt the nomenclature as well as the synthesis of rotazines and catenanes, that is the hydrogen bonded rotazines and catenanes. The formation of catenane is so facile and provides a reasonable yield as discussed above through various protocols. Hydrogen bonding gives a clue for the formation of this type of compound. Now as shown to you in the figure, the 2 rings completely fill one another's cavity and the complex is held together by the amide NHO hydrogen bond. Second macrocyclic ring is also included by assembling amide precursor by the same double bond NHO double bond C hydrogen bond, and it also causes cyclization on the included acid chloride. Now you can see this here, the synthesis of an amide based 2-catenane having the hydrogen bond. The hydrogen bonding based formation of interlocked molecules has proved to be very useful and has also been applied to rotazines. Now as shown to you in the figure, 3-rotazane is synthesized by using alkene metathesis under thermodynamic control, which causes the central double bond to break and reform. It allows the macrocycles to thread by a slipping process. Now you can see how the formation of rotazane is taking place by capping a secondary ammonium guest in this particular figure. The rotazines and pseudorotazines are also assembled by the hydrogen bonding of ammonium ions to crown ethers. Some interesting multiple times threaded rotazane type of compounds are also synthesized by similar approach. Now this approach you can see here in the figure, crown ether ammonium ion based rotazanes type hydrogen complexes. First is the 3-rotazane. Second one in the B you can see is the 3 threads in one ring and 2 threads linking to 2 rings in figure C. Next topic is the molecular necklaces type of compounds based on rotazanes and catenanes. Molecular necklaces are also catenane type of compounds in which a number of macrocycles are looped into a single central ring like beads onto a string, which forms the shape of a necklace. As shown in this figure, 3 macrocycles are looped into a single central ring. Now typically look at figure A. Considering the next figure, that is B, in this same figure, metallo macrocycle is threaded to 3 cucurbit 6 uryl beads. This compound can be described as 4Mn, that is Mn is the molecular necklaces, because there is a total of 4 different rings in this particular compound. The larger ring forms the thread, and this particular thread is commonly linked using self-assembly of a coordination compound. Now you can see how the larger ring is acting as a thread and the smaller molecules are acting as the beads, and how this finally gives the shape of a necklace. You can see the schematic representation in case of A here in this figure, that is a 4 molecular necklace, and in case of B this is showing the linking of 3 cucurbit 6 uryl molecules around a platinum 2 based metallo macrocycle. We can explain the linkage of cucurbityl uryl, that is in platinum 2 ethylene diamine complex, on the basis of molecular necklaces concept. The square planar platinum 2 ethylene diamine complex takes advantage of the affinity of cucurbit uryl for protonated diamine guest as in ligand, which links the platinum 2 centers together, and this is shown to you here in this figure. Now after having learnt about the synthesis, nomenclature and the hydrogen bonded catenanes and rotazanes and also the molecular necklace, it is time to summarize the module, students. Catenanes are interlocked to each other, while rotazanes we taught you are linear molecules which are threaded through a macrocyclic ring. Next we learnt about the nomenclature assigned through a number of rings which are interlocked to each other. Then also we learnt the synthesis of catenanes and rotazanes through statistical and direct approach of catenanes, which is also applied to rotazanes. The statistical approach, students, we taught you have been used for the synthesis of rotazanes. Catenanes and rotazanes are also synthesized by pi-pi stacking interactions. Hydrogen bonding we taught you also plays an important role during the synthesis of catenanes as well as rotazanes. And we finally learned something about the molecular necklaces, where the larger molecule forms the thread and the smaller molecules forms the beads. Now, this topic of Rotazines and Catenanes is very important under the large heading of supramolecular chemistry. And I hope this module was very informative regarding the synthesis, nomenclature and other aspects of Rotazines and Catenanes that we have covered thoroughly.